Hi, nice to meet you. Estar registrando. Well, I will show you now the measurements of the harmonics. We have tested on the transmitter. Then this is the transmitter that we will ship to you. Now we have tested this one and we have measured the harmonics. But this is the product we will send you. It's not another transmitter. It's one. So I want to show you that in this transmitter how are the harmonics with our instrumentation. Okay. Taking count, we always use, as I showed you in the previous video, and bandpass filter. This is flat over the 108 megahertz, and but there is an alteration of about 30 dB, 40 dB on the FM band, but out of band is 0 megahertz. I already showed you last time how is the curve with the network analyzer of this. Of course, we assume now this is flat. It's 0 dB attenuation in the high frequencies, about 200 megahertz, 300 megahertz, and so on. Second and third harmonics. Okay. I will show you just what happened when in the measurement when I introduce a 10 dB attenuator. This is just to show how it works, the harmonics, the intermodulation distortion of the spectrum analyzer. It must be pay always attention, because sometimes there is, for example, if there is a power meter in the system, whereas in the power meter typically there are diodes to get the forward power, the measurement of forward power, something else. These diodes can create an intermodulation distortion because they are non-linear devices. So we must pay attention to use all kind of couplers, directional couplers, or in any case couplers that have not any kind of non-linearity. So I show you again. We have this coupler that is absolutely linear, and this one is absolutely linear also in the band. Just there is some small variation. You can see we have minus 58 dB attenuation on the 98 megahertz. In the second harmonics, also minus 58 dB. In the third, minus 57. So we have only 1 dB of difference between and what is worse. And the rest we are emphasizations of 1 dB at the second and third harmonics. So there is not the measure it shows to me is worse than the real one measure. You can never use, for example, this output to measure harmonics, because this is not calibrated in frequency. This is an RF sample. Okay. So this is a kind of a measurement that must be done with a direction, with a coupler, then we know exactly how is the bend, how it must be linear. Often this kind of coupler has a very high amplification at high frequencies, so we must pay really good attention to this. This must be very well measured with a network analyzer. In any case, I will show you now. Here I'm measuring the your transmitter is 92.7 megahertz. I will show you we made exactly the same measurement with another spectrum analyzer just to show you that we can compare the two measurements. The two settings are exactly the same for the two network analyzers. We are at 10 MHz PAM, 92.7 MHz in this case. We have a bandwidth of 1 kilohertz. The same in this, we have a bandwidth of 1 kilohertz, 10 megahertz spam, 92.7 megahertz center band. Exactly, they are both set in exactly the same way. So now what we will do is to move the center of spectrum analyzer to the second harmonic, and in this case it's 108.5.4. So I put frequency 5.4 here, megahertz. Same I will do here. Frequency 4 megahertz. Okay. Now I can see here I have my harmonic, but this is not real, absolutely not real. This is because the input of this network analyzer, this input is having a big distortion because I have a signal at 92.7 megahertz, a very high signal that is creating distortion in this input. So when I go to 92.7 is, excuse me, the mean 185.4. You see, I have minus 53 dB of harmonic. But this is not real. I will check the same in this spectrum analyzer. In this case, I will put have minus 55 dB. But now take a look. If I just remember, I have minus 55. If I put 10 dB attenuator in the input, I must have minus 65 with 10 dB. But when I put it, I got minus 75. What I mean is that with 10 dB attenuator, I get 20 dB lower harmonics. Why? And this is because I'm attenuating also the distortion, the intermodulation distortion. So it is the proof that it shows me that this signal is an intermodulation distortion. It's not a real measure. It's the second harmonic of distortion of this or the amplifier of the network analyzer. You see, I just take out the 10 dB and I get $20 dB worse. So absolutely what I need to do is to put this passband that you see here is approx 30 dB, 35 from 30 to 41 dB of attenuation on the main band, and there is zero attenuation, close to zero attenuation on the passband. So I will go to the in there and see how is real the harmonic, because now I'm attenuating approximately 30 dB the main signal. So if I take it here, I see absolutely zero. I can't measure, it's too low for this spectrum analyzer, but I can measure here and I see how much is the value. It has more dynamic, but I see it's below 80 dB. You can see, below 80 dB, okay? Minus 83. This is the real value of this harmonic. And this spectrum is almost invisible because I have 80 dB attenuation. It's almost not possible to see. The mark is a minus 80 dB, but the harmonics is minus 83. The CM is, if I may measure with the third harmonic. Excuse me, I will show you now. If I put it here, I will go to 92.7. 92.7. And you can see how the main carrier is attenuated about 40 dB, as I showed you before. If I disconnect this one, the passband, you see, this is my carrier frequency. Now I put it, I attenuate just only the carrier frequency, and if I go again to I see there is nothing. Okay, so this is the I show you, this is the amplifier. We are at 1 kilowatt, okay, and 92.7, and this is the amplifier it will arrive to you. As I show you, we are using two instruments different to make this measurement. We are using a calibrated coupler. We are using a calibrated passband filter, and these are two spectrum analyzer. We are connected through the web page on the transmitter, just to test also the web connection. This is exactly what you use for the transmitter. Okay, thank you. At the next time.